Hi everyone, welcome back. I'll just give a few more minutes for participants to join. Get started. All right. Well, welcome back everyone. Good morning. We have a very special session for you today, and that one that sits right at the intersection of quantum optimization and state-of-art research being done in the field. And for that, we have with us Dr. Stephen Jordan, who is a quantum algorithms researcher at Google Quantum AI. And his career has spanned some of the most influential institutions in quantum computing, NIST, Microsoft, and now Google. He received his PhD in physics from MIT in 2008, and many of you might have already known him as the author and maintainer of the Quantum Algorithm Zoo, which is a comprehensive catalog of quantum algorithms that researchers around the world use daily. And today, Dr. Jordan will be talking about his work on the decoded quantum interferometry, which is an exciting new method in the quantum algorithms for optimization area. And there is a lot of buzz in the community on how this really genuinely opens a new path towards getting quantum speedups for optimization problems. And I'm very excited to learn more about the topic today. Please join me in welcoming Dr. Stephen Jordan. Over to you, Stephen.
Thank you. It's great to be here. Let me just share my slides. Are those showing for people?
Yeah.
Great. Okay. So I'll be talking about optimization by decoded quantum interferometry. And so first we can ask why we care about optimization problems in the first place. And I think that's best illustrated with an example. One that I've encountered in the real world is the capacitated vehicle routing problem with time windows, which is studied under the name CVRP-TW. And it's a hugely important problem because annually for trucking, the total expenditure is about 2.5 trillion US dollars, and the total carbon dioxide emissions is around 2 trillion kilograms of CO2. And we know that the routing and dispatching problems that are being solved by computers are not being solved to exact optimality by the existing software tools. So this is a problem where you have many packages to deliver. You have to allocate which packages will be delivered by which trucks. And then for each truck, you have to choose in which order they'll make the deliveries. So it's kind of like the traveling salesperson problem, but even more complicated. And it's very hard to find the truly optimal solutions. We're not doing it. And even improving, so you can see from these numbers that even improving the efficiency of the allocation, the kind of dispatching and routing problem by 1% would be worth $250 billion and 200 billion kilograms of carbon dioxide emissions saved. So I think this is just one illustration of very many kinds of optimization problems that arise in the real world that have huge impact because of the scale of the processes to which the optimization is being applied. And so I think that these problems are kind of very inspiring. You can really quantify the impact you're making. And so one question we can ask is whether quantum computers might help. Now, it's pretty difficult to directly attack these problems with quantum computers. So oftentimes in the foundational research into new optimization algorithms, we look at problems that are ultimately much simpler and much more mathematically cleanly defined. And those form a nice test bed to learn techniques that we could later worry about applying to these very complicated problems, such as the capacitated vehicle routing problem with time windows. And so it's a little bit similar to in biology. They like to do experiments with mice. It's not necessarily because they directly care about mouse healthcare. It's because mice are a nice, easy to work with kind of model system that can be used to learn things that could be applicable to humans. And so one of the standard sort of test beds for optimization is the max-XORSAT problem. And it's a very nice, clean, simple mathematical problem where we're given some matrix and we're given some vector. And the matrix is non-square. So the number of rows is more than the number of columns. And then everything's taken mod 2. And so all the entries in this matrix and this vector are just bits. And we put our decision variables, which we call x, of this vector x. And we want to choose these decision variables so that bx is as close as possible as to our target vector v, as measured by Hamming distance. And that's the whole problem. And so we could sort of visualize this as a lattice problem, but mod 2. So that's what we'll use. We'll start with the motivation of looking at real world optimization problems, but as our test bed, we'll use this more abstract, simple problem and its variance. And so I think people have, for a long time, more than 20 years, been quite interested in the question as to whether quantum computers can achieve exponential speedup for optimization. And there are several reasons for this. One is that optimization problems have the right general characteristics for exponential quantum speedup, in that these tend to be not really big data problems, but rather big compute small data problems. And so the limiting factor is not the input-output bandwidth of the computers, but rather the bottleneck really is compute itself. A more formal statement is that if you want to have an exponential speedup for a computational problem, you need the computational problem to take exponential time to solve in the first place, so that in the sense that the number of computational steps to solve it should be exponential and the number of bits to specify the problem. Now, one thing you might worry about is that many optimization problems are NP hard, and we don't expect that NP is contained in BQP. So for complexity theoretic reasons, we don't actually expect that quantum computers can find exactly optimal solutions to worst case instances of these optimization problems in polynomial time. But that doesn't mean that we have to give up, because we can ask a different question, which is whether polynomial time quantum algorithms can find approximate solutions that would require exponential time to find classically. And so maybe the best classical algorithm finds a solution that's 80% optimal, but the best polynomial time quantum algorithm finds a solution that's 85% optimal. And so that's actually potentially an exponential speedup, because oftentimes what happens is once you go past the level of optimality achieved by the best polynomial time classical algorithm, you just have to fall back on classical algorithms that are sort of variations of brute search and take exponential time to run. So it could be that achieving 85% optimality classically would take exponential time. And so even if you have a small advantage in optimality, it could be an exponential advantage in runtime. And so because optimization problems have so many important economic applications, and because they have these nice computational properties that make them tempting, they've been studied a lot in the context of quantum computing. But I think an underappreciated point is the degree to which we still don't fully understand the power of quantum computers to help with optimization problems. There aren't so many examples where we can convincingly argue for speedup, despite searching for a long time. And so there has been very interesting prior work on quantum algorithms for optimization, especially adiabatic optimization and the QAOA algorithm. And both of these came from the research group of Eddie Farhi, and he actually was my PhD advisor. And one thing I learned from him was that it's very useful to have some source of physical intuition to help guide the search for new quantum algorithms. And for QAOA and adiabatic algorithm, the source of physical intuition is Hamiltonians, or more broadly, it has to do with the fact that in nature, many systems naturally converge to low energy states, just as if you sort of nudge a rock on a hillside, it's going to roll down the hill and not up. And we can kind of try to take advantage of that to use quantum mechanics to solve optimization problems, where we sort of map the cost function that we're trying to minimize to an energy function. And that's been fruitful in certain ways, but here we're doing something that's outside of that box. We're using a different source of physical intuition, which has more to do with interference patterns. So what we observe is that the cost functions or objective functions of many commonly occurring optimization problems have actually very sparse Fourier spectra. So if you have some function on n bits, then in principle there's 2 to the n components in its Fourier or Hadamard transform. But if you look at, for example, the max-XORSAT cost function, then the number of non-zero components in its Hadamard transform is only equal to the number of clauses. So typically that's just linear in the number of bits. And so that's a huge difference, and you can try to take advantage of that. And so ultimately, what we do with decoded quantum interferometry does take advantage of that by using a quantum Fourier transform to obtain constructive interference on solutions where the cost function is lower, or if you think in terms of objective functions, where the objective function is larger and achieves destructive interference elsewhere. And this idea is not completely new. It actually has deep roots. there was a flurry of work back in the early 2000s by Dori Taharanov, Amnon Tashma, and Oded Regev, which looked at using the quantum Fourier transform to interconvert between different kinds of lattice problems. And one of the most fundamental lattice problems that's sort of a hard computational challenge is given a high dimensional lattice, in other words, a integer linear combination of a set of basis vectors, sort of illustrated on the left over here, that you want to find one that's very close to the origin. So in particular, you might try to find the shortest non-zero lattice vector. And so if you had a quantum superposition over the lattice, where the amplitudes were larger on the short lattice vectors than on the long ones, then you could just measure that in the computational basis, and you would preferentially sample from short lattice vectors. So that would solve your problem. But then the question is, all right, well, how do you actually efficiently make such a superposition using a quantum circuit? It's not so easy to see how to do that. But one thing we know we can do is we can do Fourier transforms. We know efficient quantum circuits from that, which come originally from Peter Shor. So if there's some state you don't know how to make, you could say, well, let's see if we know how to make its Fourier transform, because if we can figure out how to do that, then we just Fourier transform back and we get the state we wanted. And so if we look at the Fourier transform of this state, which is a weighted superposition over a lattice, it turns out that there's something called the dual lattice. So there's another lattice which is dual to the first one. And the Fourier transform of the picture you see on the left is the picture you see on the right. So it's a superposition over the dual lattice, but instead of delta functions at each point, you have little peaks whose shape is the Fourier transform of the shape of the envelope function on the left. And so now we have a different problem. If we could make the state on the right, then we're done, because we can use the Fourier transform to make the state on the left and solve our original problem. And it turns out that making the state on the right can be boiled down to something called a bounded distance decoding problem, where if we're at some point in space, which is within the support of one of these little peaks, and we can figure out which lattice vector from the dual lattice constitutes the center of that peak, then that's the bounded distance decoding problem. And if we have a solver for that, we can make this state on the right efficiently. So basically what we've done is we've taken the problem of finding a short vector of the original lattice to finding a nearby vector on the dual lattice. But on the dual lattice, we're given the promise that our nearby vector is not too far. So like if we don't have to solve the bounded distance decoding problem if we're way out far from the nearest dual lattice point outside the support of these peaks. Now, back in the early 2000s, this kind of reasoning didn't lead to any algorithmic quantum speedups. The problem is, as you make the distribution more narrowly peaked around the origin on the left, then these peaks on the right get broader. It's just like Heisenberg's uncertainty principle. The Fourier transform of a narrow peak is a broad peak. And so as these peaks on the right get broader, then this bounded distance decoding problem gets harder, because we might be far from the nearest dual lattice vector. And so the difficulty of these two problems that we were converting between sort of moved in lockstep as we varied this radius, the radii, these sort of reciprocal pair of radii on the two peak shapes. And in order to gain advantage from this Fourier transform, we need to find some scenario where these difficulties don't move in lockstep. And then it becomes true that with this sort of magical quantum ability to hop back and forth between the problems using a Fourier transform, then you actually find advantage. And that's how things stood for about 20 years until recently, over the past 5 years or so, there's been a kind of renaissance in this type of thinking. And this time around, we apparently do have some quantum advantages that we've found. And so decoded quantum interferometry is sort of part of this renaissance of this type of thinking. There are also some other works from the group of Marc Gendry and from the group of André Chailloux, which also achieve some new results with this kind of thing. And so one thing you might ask is, what's different this time around? And I think there's really two differences with the current wave of work. One is that we're focusing our attention more narrowly on more specific classes of lattices and codes that have more structure to them, not just purely algebraic, not just purely geometric structure. So in some sense, you could say we're setting our sights lower than what was done in the early 2000s, where they wanted to find one algorithm that just breaks all of these problems. And now we are looking piece by piece. Well, what if the lattice has sparse generator matrix? What if the lattice has a certain kind of algebraic structure? What if the lattice has this property or that property? And for each property, we can ask, does it change the difficulty on one side of this duality between these pair of problems more than it changes it on the other? And if so, then this ability to hop across can gain us advantage. So that's one thing that is different now. And the other one is we have more insight into actual quantum algorithms for this bounded distance decoding problem, as opposed to just merely swapping in existing classical algorithms. And so in the specific case of decoded quantum interferometry, we consider lattices that are over finite fields, such as the integers mod p, where p is a prime. So the terminology is a little different here. Instead of calling them lattices, we call them codes. That's because they have many applications in classical error correction, but conceptually they're kind of the same thing as lattices. And we also look at more general objective functions instead of just short vectors that are near the origin. But the most important difference, those are sort of just technical differences. The key difference here is we consider two forms of structure in the code that can affect the ability of this pair of dual problems. One is algebraic structure, and the other is sparsity of the generator matrix. And these we don't just impose by fiat. It turns out that they arise naturally in certain contexts, which we'll see shortly. So the first example is the optimal polynomial intersection problem. And the problem is we are given target points, and we want to intersect as many as possible with some degree n polynomial. It's a univariate polynomial, and here n is less than m. And we take all these equations mod p, or if you prefer, you can think of it as we're working over the finite field fp. And so because, you may remember that if you have a polynomial of degree n, you can always exactly hit n target points. But here, the number of target points we're trying to hit is much bigger than n. And so we probably just can't hit them all. And that's what makes it a non-trivial optimization problem. We're trying to hit as many as we can. And in fact, we can define the problem a little bit more generally. We can say, well, maybe we don't need to hit these points exactly. Maybe we need to get within, plus or minus 5 of our target point, for example. And so that's illustrated here with like these little orange colored segments, these vertical segments. And in fact, we don't even need them to be contiguous segments. We could just say, well, there's some subset of this finite field that we want to hit for a given input value to our polynomial. And so that's illustrated with these kind of broken segments. So that's a very general kind of problem of trying to hit various targets with a polynomial by adjusting the coefficients in the polynomial. And the nice thing about this problem is, although it doesn't superficially look like it, it can be phrased as kind of a problem about a linear code over fp. And the problem that's dual to that via a Fourier transform ends up being a bounded distance decoding problem for a dual code to the one you started with. And the decoding problem that you reduce this to via quantum Fourier transform turns out to be recognizable as a Reed-Solomon code. And when you find out that this is a Reed-Solomon code, it's very good news, because Reed-Solomon codes have excellent information theoretic properties and excellent classical polynomial time algorithms for decoding them, which go back all the way to the 1960s, if I remember correctly. And so we can just use these decoding algorithms to prepare this state that we want to prepare on the dual side. Then we do a quantum Fourier transform and get the state we want on the primal side and solve our original optimization problem. And this problem that we solved, the optimal polynomial intersection problem, this name optimal polynomial intersection is a name that we made up, but it's not really a problem that we made up. So what it turns out is that various kind of special cases of this problem have already been studied in many different contexts. So in particular, in coding theory, this is called list recovery for Reed-Solomon codes. In cryptography, this is called noisy polynomial reconstruction. There are some math papers about it where they call it something else. So it's a previously studied problem, and there's a number of papers studying classical algorithms for solving it that we can compare to. And so if we just plug in some specific numbers, basically the example we studied first was we just set m over n equals 10. So the number of constraints is 10 times the number of decision variables. So it's a highly over-constrained problem. In other words, here the number of targets we're trying to hit is 10 times bigger than the degree of the polynomial we're trying to hit them with. And we set these target sizes to be pretty broad. So it's actually each of these broken segments we're trying to hit is half the field. And so anyway, in this regime, the algorithms that are known in the literature, the classical algorithms, basically break down, and all you're left with is very brute force style of classical attacks that get very poor approximations. And so for those parameters, what we find is our quantum algorithm satisfies almost 72% of the constraints, and the best classical algorithm we know about that runs in polynomial time satisfies only 55% of the constraints. And there was nothing that special about these parameters of m over n equals 10 and r over p equals half. We could make other choices and get similar kinds of advantages. And so as far as we know, this is an exponential quantum speedup for this optimization problem. And so this is something that people have been, the kind of thing that people have been searching for a long time. And so a lot of excitement got started by this discovery, and we published this in Nature in 2025. And so I think when you find something like that, the natural hope is that maybe this is the tip of an iceberg. So it's a very dramatic speed up, but the next question is this just an isolated example, or is it the first hint of a broader class of speedups? And I think people always have these kind of hopes when a new exponential quantum speedup is found. Certainly when Peter Shor discovered his factoring algorithm in 1994, I think there was a lot of hope like this. And to some degree, it was realized that, in fact, Shor's algorithm could be generalized to solve some other problems, such as solving Hell's equation, finding unit groups and class groups of algebraic number fields, and so on. So with decoded quantum interferometry and the OPI problem, we can ask the same thing. Is there anything else in the neighborhood of this? And so I think there are a few natural directions one could go with this. One way you could go is you could just say, well, what we basically did is we took these reductions between dual pairs of lattice problems that were known since the early 2000s, and we applied them to problems with algebraic structure, which hadn't been done back then. And we kind of hit the jackpot with that. And so we can ask, well, what about other kinds of algebraic structure? And in fact, it is true that we now know you can impose other kinds of algebraic structure besides the algebraic structure of the OPI problem and get similar speedups. So I, for example, have a paper with Andy Gu showing that some problems from algebraic geometry can be attacked this way. A different direction you can go is, well, these algebraically structured problems are a little bit specialized. It'd be nice if we could move more in the direction of industrial problems like, say, vehicle dispatching and routing. Can we take at least a baby step in that direction? And in my opinion, a baby step in that direction is to look at problems that do not have algebraic structure, but instead just have sparsity. They have the property that each constraint only involves a modest number of variables. And this is very typical. So for example, each truck has a certain capacity, so that's a constraint only on the packages that go into that particular truck, for example. And the max-XORSAT problem is sort of a nice mathematically abstracted example that captures the essence of that property. And for that, we already know that if you just take the state-of-the-art classical decoder for the resulting codes, which are LDPC codes, it's not enough. And so you really need to design better decoders to attack these more industrial problems where you only have sparsity structure and not algebraic structure. And I think a third direction you can go is to ask whether DQI can be generalized to find low energy states of quantum Hamiltonians instead of just classical cost functions. And in fact, there are ways to do this. And I have a paper co-authored with Sasha Schmidhuber and some other authors which explores this. So among these directions, the one that I'm currently most excited about is this question about can we attack these sparse, unstructured problems using better decoders? And I think it's a very provocative question. So for example, Scott Aronson, I spoke to him about this, and he at least verbally stated the informal conjecture that we won't succeed when we attempt this, that super polynomial or exponential quantum speedups for optimization will only be found if you have algebraic structure in your problem. And so far, we have not succeeded in refuting Scott's conjecture. But on the other hand, I don't consider it a reason to give up. I consider this a challenge. And so one of the nice problems you can work on is, as I said, max-XORSAT, which really has this same, is recognizable as a lattice problem. And so the same techniques can be applied with quantum Fourier transforms. And so if you start with a max-XORSAT, then it gets reduced to the decoding problem for a code where the parity-check matrix is the matrix B. So basically, we start with a problem on the primal code where B is the generator matrix, and we get a decoding problem where B is the parity-check matrix, whose kernel defines the code, instead of whose image defines the code. And the nice thing is LDPC codes, these ones with sparse parity-check matrices, are well studied, and they do have quite good decoders and nice information theoretic properties. So that's a source of encouragement. And so then the next thing you need to ask is, well, if we're converting two kinds of coding problems, what's the relationship between them quantitatively that we achieve? And so we saw in the lattice problems that if we need a narrow peak was dual to a broad peak, whose width was sort of basically the reciprocal of the peak we started with, and that related how good of an approximation we get to our original optimization problem to how far we need to decode out to in the dual decoding problem. Well, we have the same question here. And it's really just a question of Fourier analysis. And, in our paper, we prove that the answer to that question is as shown in this formula. So that basically, if you can decode out to a larger radius L on the decoding problem, that allows you to get a better number of satisfied constraints S on the optimization problem. And this traces out we call this the semicircle law because it traces out the shape of a semicircle. So once we have this Fourier analysis problem solved, we have the semicircle law in hand, then that gives us a nice research program that we can carry out. Because even though we don't have quantum computers large enough to carry out these experiments, we can analyze things theoretically. Because we choose an ensemble of instances, we test our classical optimizers on them to find out what's the score that we're trying to beat in terms of approximate optima. We write down the dual LDPC code, and we can test classical decoders on that. Then how many errors we're able to correct with those classical decoders, we can feed into the semicircle law, which tells us what approximate optimum we would achieve with a quantum computer. And so we just compare this approximate optimum achieved with a quantum computer against the approximate optimum achieved by the classical optimizers and see who wins. If quantum wins, we're done. We just, we celebrate, it's party time. We celebrate, we publish our paper, everyone's excited because there's been long demand for quantum advantage and optimization. If classical wins, well, we can try again. We can look at a different ensemble of instances. We can look at a different decoder for the dual problem and tinker around until we can try to find a win. So this is something we tried by just sort of dropping in the standard state-of-the-art classical LDPC decoding algorithm. And what we find is this doesn't ever actually win. So we looked at sparsity parameters K and D. So each row of the matrix has K non-zero entries. Each column has D non-zero entries. And we scanned through all these different KD pairs. And we could never find an example where if we just take DQI and swap in the state-of-the-art classical decoder, that we actually beat the sort of team of classical optimization problem algorithms that we're competing against. And so this was a rather disappointing result. And so the next thing to ask is, well, can we improve upon the decoders that we put in there into our DQI algorithm? And we know that information theoretically, it's totally possible for DQI to win on these problems, even when restricted to a classical decoder, at least for some KD pairs. So here's kind of a diagram of that if you just you plug in the Shannon bound into the semicircle law, and you say, with an information theoretically optimal decoder, what would we do? And we compare that against the classical optimizers. There's a big region in that space where we'd come out ahead. That's this blue region here. Now, for some KD pairs, even with information theoretically optimal decoding, we still wouldn't win, and that's this orange region. So we can take that as a challenge for the design of classical decoding algorithms. Another thing we can say is, well, this decoding problem, actually, the errors are in coherent superposition, and that's advantageous from an information theoretic point of view. And so then instead of being limited by the Shannon bound, we're limited by the Halevo bound. if we have some decoding algorithm that's fundamentally quantum and takes advantage of that coherence. And there, this situation is even better. There's no orange region on this diagram, as you can see. And so for every KD, it's actually information theoretically possible quantumly to beat the classical optimizers that we've compared against so far. But, actually achieving these or even approaching these information theoretic limits using algorithms that are efficient is a hard problem. And one of the interesting ways of attacking this problem is using locally quantum decoders. And there's an old trick from the information theoretic literature that you can use for this. One of the things that I think is very interesting about this subject is that it brings together quantum algorithms and quantum information theory, and we can start to harvest some of the information theoretic tricks to put to algorithmic use. And one of the neat tricks that's been known for a very long time is something called unambiguous state discrimination. So let's say we have a qubit, and if we knew ahead of time that's either in the state ket 0 or ket 1, and we want to know which, we just measure in the computational basis. No problem. But now suppose there's a little bit of error. We instead of the ket 0, there's a little epsilon amplitude on 1. And instead of ket 1, there's a little epsilon amplitude on 0. And so now these states are not orthogonal to each other anymore. So we could just still measure in the computational basis, and we'd have some probability epsilon squared of getting it wrong. And maybe epsilon is small, and so maybe that's okay, but that's not the only thing you can do. It turns out there's another thing you can do that's allowed by the laws of quantum mechanics, which is to devise a 3-outcome measurement, which will say 0, 1, or I give up, basically. And if the measurement says 0, then you definitely had the ket 0 plus epsilon ket 1 state. And if you get 1, then you definitely had the other state. And so even though these are non-orthogonal states, you can sometimes learn about them with absolute certainty. But the price that you pay is that sometimes the measurement just gives up, and this probability of giving up, of course, is dictated by the degree of non-orthogonality of these states. And so if you take this and apply it to decoding problem, what you can see is you've actually taken the bit flip errors and converted them into erasure errors. So you have some code word, a string of ones and zeros, and now some of them you know, and some of them you don't know. But you know which ones you don't know. They're sort of known unknowns. And so now your decoding problem you can think of as being just a linear algebra problem. You have a parity-check matrix that defines a bunch of linear equations, and some of the things that enter in those equations are knowns, and some of them are unknowns. And so you can just use linear algebra to solve the resulting system. That's the appeal. That's part of the appeal of this USD measurement trick to convert bit flip errors to erasure errors. Now, this was studied by André Chailloux and Jean-Pierre Tillich in the context of DQI or Regev type reductions. And what they found is that this did not lead to quantum advantage. It only allowed you to match the performance of an existing classical algorithm called Prange's algorithm. And actually, in a way, that remains a little bit of a mystery why there would be an exact match between the performance of a classical algorithm and a quantum algorithm that looks nothing like it. So our most recent work has been to extend this. We joined forces with André Chailloux's group, and we sort of generalize this idea where we apply these unambiguous measurements to blocks of qubits instead of one at a time. And we choose the blocks of qubits to line up with the parity checks so that we have some a priori knowledge of the bit strings. Basically, the parity check tells us the overall parity of that block of qubits. So now the number of bit strings, the number of states we're trying to distinguish between is cut in half. And that's quite advantageous for the design of these measurements. And so when we try this, what happens? Well, we actually do make more progress. We finally find some KD pairs where we beat both Prange's algorithm and simulated annealing, which is something that we had, as I've mentioned before, sort of bashed our heads against for a very long time without achieving. Once you find something like this, the next question is like, well, we better sort of red team this very carefully. We better really look carefully at competing classical algorithms to see if we're truly beating all of them or just some of them. And in fact, eventually what we find is that we can, again, find a classical algorithm that exactly achieves a tie with our quantum algorithm. And this classical algorithm really looks nothing like the quantum algorithm. And it's this mysterious phenomenon happening again. Essentially, the nature of the classical algorithm that achieves a tie with what we have here is something we call turbo-Prange, which basically is you use Prange's algorithm, which is a linear algebra-based method, followed by greedy bit flip updates. So one of the conjectures my collaborator Noah Shuddy has made is that if we do any decoder based on measurements on blocks of order log n qubits followed by Gaussian elimination will yield a DQI algorithm whose performance is matched by some corresponding classical algorithm. And so that's sort of a conjecture that we're still investigating. We have not found any counterexample to it. But what that leaves us with is, I think, a vast space of attacks remaining. So my current research really focuses on other kinds of quantum decoding algorithms, which do not use this same trick of unambiguous state discrimination measurements, but use various other tricks. And we're competing those against the various classical optimization algorithms for sparse problems such as max-XORSAT. And so I understand that this meeting tends to have very lively questions. So I'll try to just summarize and wrap up and leave plenty of time for those. And so I think the takeaway messages, first of all, decoded quantum interferometry achieves a super polynomial speedup over known classical algorithms for this optimal polynomial intersection problem. Now, one thing I like to emphasize is that there's no proof that a better classical algorithm for the optimal polynomial intersection problem couldn't exist. So that's one of my motivations in giving talks like this. I want to lay down the gauntlet to all the classical computer science scientists out there. Consider yourselves challenged and provoked to see if you can outperform the approximation ratio we achieve on this OPI problem. I've been going around provoking the classical computer scientists for about 2 years now, and so far our advantage has held up. And so the longer it holds up, the greater confidence we gain that maybe it's in fact fundamental. But there's always room for a surprise. I think a second takeaway is that simple quantum decoders, such as these ones based on unambiguous measurements, are already yielding better results than the state-of-the-art classical decoder in the context of DQI. So if we just swap in belief propagation, that's sort of the most obvious thing to do. It's really, for a classical algorithm, it's really good, and it's been, optimized and honed and studied for decades. And already, if we just sort of hack together some kind of simple quantum decoder, it's already outperforming that. Not by quite enough to give us quantum advantage, but I think it's noteworthy that it's outperforming already. And so I do think that there's a lot of promise in looking at quantum decoders, developing quantum decoders for the purpose of solving optimization problems. And then we have these slightly more theoretical questions, such as Scott Aronson's conjecture and Noah's conjecture. But I do not accept Scott's conjecture as being definitely true. I think it's something, I take that as a gauntlet that he's laid down for me. Can we refute him on that? And then lastly, as I mentioned, we have this sort of mysterious phenomenon about weird synchronicities between the behavior of classical and quantum algorithms that we really don't understand, which is one of the many things that would be interesting to dig into further. So with that, I will kind of conclude. I would like to thank you for your attention. And also I'll thank my large group of collaborators on this body of work, who are listed here. These are not all co-authors on the same paper. These are the union of the sets of co-authors on the various papers that I mentioned today about DQI. And as you can see, it's a large group, and I also invite all of you to start thinking about this topic. I think it's a very fruitful area with many unsolved mysteries. And thank you for your attention.
Thanks, Stephen. This was great. Thank you for such an excellent talk. And we have a lot of questions. I'm going to read them out to you. The first question from Arushiraj. Does the property of the 1 over R spikes similar to all the spikes on the R plateau, though they are spreaded at some distance from each other?
Yeah, so maybe I'll show this picture again. Let me just share my screen. Okay, so here, is that showing?
Yep.
Yeah, so here on the right, we have all these little spikes centered at the points of the dual lattice. And so as we make the peak narrower on the left, the peaks on the right will become broader. Eventually, the peaks on the right will become so broad that they overlap. And now it just looks like one big plateau across the whole space. And so what does that mean to us conceptually or computationally? Well, at that point, when the peaks on the right cover the whole space, it means we no longer have a promise that the point we started with in this bounded distance decoding problem is actually close to the dual lattice. It could just be anything. And so now it's not the bounded distance decoding problem anymore. It's just the decoding problem. And that problem is just very, very hard. It becomes NP hard, in fact. And so basically that happens at the same point that on the left-hand side, the peak is so narrow, it basically encompasses nothing other than the shortest and second shortest vectors of the primal lattice. And so that's, I think, an illustrative extreme case. When you crank down the width of the peak on the left so narrow that you get an NP-hard problem of exactly finding the shortest non-zero vector, then on the right, the peaks become so broad that they cover the whole space, and you have no bound on your distance from the lattice, and you're just faced with the completely general decoding problem from an arbitrary point in space, which is also NP-hard. And so that's a nice sort of extreme endpoint that illustrates the kind of lockstep movement of the difficulty of these two problems.
Thank you. Another couple questions that I'm going to combine. So can you talk a little bit about this specifically, why Fourier transform was used here, and what makes it the one that has what property of Fourier transform makes it?
Yeah,
Yeah.
that's a nice question. I mean, I think there are several nice things about the Fourier transform. One is that you get this kind of the same structure on both sides. If you start with a lattice, you take the Fourier transform, you get a dual lattice. And so this is not, I mean, in some, you could say like, well, what about other transforms? Do you have something analogous to this? So the thing about a lattice is there's a natural notion of taking two vectors and adding them together. And then when you do, you get another element of the lattice. So there is a notion of addition, and the lattice is closed under addition. And then that's true on both sides of the Fourier transform. And so if you look at more general objects, like let's say a non-abelian Fourier transform, you don't really get, so on the primal side, you still have this notion of addition, but on the dual side, you have irreducible representations of the non-abelian group, for which it's not clear what the notion analogous to addition would be. And so this picture of lattices kind of breaks down. The other thing that's nice about the Fourier transform is there's a convolution theorem. And so that if you take the Fourier transform of the pointwise product of two functions, then that's equal to the convolution of the Fourier transforms of those two functions, and vice versa. And this convolution theorem is a very nice lens for looking at the whole thing that's going on in DQI. So if you look at that same picture I showed many times, let me just pull it up once more. You can see on the left, you have the pointwise product of a Gaussian envelope function with the lattice. On the right, you have a convolution of a Gaussian peak function with a dual lattice. And so that's really the convolution theorem at work. And in this paper by Yamakawa and Jandry from 2022, they have an algorithm that is actually quite similar to DQI and solves a problem that's kind of related to the OPI problem. They're looking at an oracular problem, so it's a little bit different in that sense. And also their alphabet is exponentially large, which is a very different regime from what you'd see in optimization problems. But their way of describing it is a little bit complementary to ours. They describe the whole thing in this convolution theorem language where basically they say, we have two kinds of constraints. We want to impose them both. So that means we want the pointwise product of the indicator functions for those two constraints in our quantum state. And so if you want that, then you could say, well, on the Fourier dual side, what you need to do is a convolution, and that naturally leads to a decoding problem. And so those are sort of some special properties of the Fourier transform that help us. And, you can ask like, well, what about a wavelet transform, or what about a Legendre transform, or this or that? And it's an interesting thing to think about. I'm not sure whether it will lead to new quantum algorithms or not. So far, we haven't gotten anywhere with that, but I do think it's conceivable that this line of reasoning could lead to an interesting.
Thank you. A question from Dharalakshmi. What properties of OPI make DQI perform well, and how can we identify other problems that have similar properties?
Yes, well, I can tell you the history of how we found that is a little bit backwards from the way that makes the most sense to describe it pedagogically. So really what happened is we wanted to use DQI to gain quantum advantage on max-XORSAT. And I showed that little thing where you go around the loop and you try to win. And we did that for months and months and months, and we would never win. And finally, out of kind of desperation, we started to be worried that like maybe there's some theorem that we don't know how to state or how to prove, which is secretly blocking us. There might be some like conservation law that says telling that you can never win. So we tried to construct at least a counterexample to such a conservation law by just putting something in on the dual side, which we knew had very good decoders. So we just took Reed-Solomon codes and put them in on the dual, and then asked like, okay, what's the optimization problem that's dual to that? And are we achieving, no matter how contrived that optimization problem might be and how artificial, and are we achieving advantage on that? And so that was the idea. And it was only after the fact that we realized that the optimization problem we got was not so contrived and artificial. In fact, if you look at it the right way, you could see that it was kind of a very normal looking polynomial regression problem and had been studied in many papers already. And so that was how we arrived at it. And so you can try following that same procedure. You can take various algebraic codes and just plop them in on the dual side, ones that are known to have great decoders, and then see what optimization problem is dual to that by a Fourier transform, and try to squint at it in different ways and see like, oh, is it actually a natural problem somehow? And so that is, one example of that approach is what Andy Gu and I did in our paper about sort of putting Hermitian codes on the dual side and getting an algebraic geometry problem on the primal side.
Thank you. It was really nice getting an insight into how you think about this research process, and it's such a non-linear process. It's kind of like nice hearing your story with it. Maybe we have time for one last question. So yeah, a question from Sai Teja. If DQI allows us to simplify these complex problems into a dual domain that classical computers can easily decode, why do we actually need a quantum computer after the Fourier transform step is done?
Yes, that's a good question. Well, so it turns out that for this problem in the dual domain, the decoding problem, we use a classical algorithm, but we need to run it in superposition on a superposition of many different instances of the problem at the same time. So we actually have to take on that classical algorithm and implement it as a reversible circuit and run it on the quantum computer. So in some ways, this is unfortunate because when you take classical algorithms, especially ones with a lot of floating point operations like belief propagation, and recompile them into reversible circuits, they end up being kind of large reversible circuits typically, and which is not ideal from a practical point of view. But so that's what happens first of all, but the other comment is, I would say, yeah, sometimes when we study these things, we get algorithms that are pretty impractical, but we consider it sort of a first step. Like if you can find something that scales asymptotically better in terms of its, how does the number of gates scale with the problem size? If you can find advantage in that, then later you can try to hone it and whittle down the sort of the constant factors that go in front of that and make it into a more practical algorithm. And so we do have a paper. There was one that was led by Tanuj Qatar that I was involved with, where we go through that process for the OPI problem and find out the constant factors and really what do the circuits look like concretely. And actually that came out pretty good. So it turns out that it's not a NISQ-friendly algorithm, but actually the size of quantum computer that you would need to solve a classically intractable instance of OPI is actually a bit smaller than the size of quantum computer that you would need to solve a classically intractable instance of factoring using Shor's algorithm.
Yeah. Okay. Thank you so much. I really want to thank you for taking the time to come talk to us today about this very exciting approach, and also for kind of inspiring our participants to kind of think about these open challenges that, are still there and that needs to be solved. Thank you so much for taking the time, Stephen. I really appreciate it.
Thanks for having me.
Thank you. We have another session for you today. I'm just going to give a moment for our speaker to join. I see him on the call. Give us a minute.
Right. And in the meantime, maybe you can share what you loved about Stephen while we wait for Vimal to come join us. Maybe put on Discord. What are some things you really loved about the past session?
Yeah. Ruchiraj says it was interesting but quite advanced. And I agree with you. It was kind of a lot. But it's kind of interesting to see all these new techniques coming up that are alternatives to quantum annealing approaches or QAOA, and it's really exciting to learn about it.